Correct. For those who haven't met me, Anthony Smith. I'm currently the chair of airworthiness for GFA, amongst my many other crimes. I'm an aerospace engineer, as Craig pointed out, and I spent a lot of time out at Edinburgh supporting the Air Force's P3 fleet. I also own a Bergfalk 4, which has been under having a survey for quite a while. And when they say it's a 10-year survey, I'm pretty sure it didn't mean it was supposed to take 10 years, but it's getting pretty close to that. When Craig asked me to do this presentation, he said he really wanted it very simplified and not to use as few technical terms as possible. I've taken that to heart, and I'm going to try and do this presentation without using one equation on the slideshow. We'll see how I go. Okay, I thought I was sharing the screen. Half a second, I've got some Zoomy things happening here. Yeah, half a second. I can focus on, am I sharing? Good. Yes.
If there are no equations, would this be a balanced report?
I'll let you decide on that, and you can tell me at the end. And please excuse me with the reading glasses. I need to read the screen, and I like to make eye contact with the audience, so you'll see those bouncing up and down quite regularly tonight. So what I'll cover tonight, I've got a couple of things to cover in the introduction. One is, of course, why do we care? I'm going to mention Isaac Newton and his third law because I make reference to it later on. It's quite important. I'll talk a little bit about turbulence, because when we start talking about turbulence in terms of drag and boundary layers, people get very confused about what exactly I'm talking about. So I'm going to talk a little bit about the various forms of turbulence people have encountered during their flying. And then I'll start going into what is drag. What is a good definition of drag in its simplest form? And I'll talk a little bit about profile drag, and I've lumped friction in with profile drag, induced drag, and some other little odds and ends at the end there. Please feel free to ask questions along the way, and I'll answer them as best I can. But don't expect any equations. So why do we care about drag? Why is drag important to us as sailplane pilots?
Slows us down.
Slows us down.
It reduces the energy.
It reduces your energy. Any other ideas? Makes you sink quickly. Drag defines our gliding performance. The performance of the sailplane is measured in lift over drag. Lift equals weight. Drag is the thing that determines our glide ratio at whatever speed we're flying at. So that's why we care about drag. It determines our glide slope. So if we can reduce drag or minimise the drag, we're going to get more performance out of our sailplane. And over the last few decades, we've seen quite an improvement in sailplane performance and handling. So just bear with. Yep. So I've got to introduce a few basic concepts that I'm going to be mentioning later on. And the one I want to cover here is Isaac Newton and his third law. I've got the first two up there so people can read them if they want, but the third law is the important one, and that's the mutual forces of action and reaction are equal and opposite. This is the one they trot out when you fire a gun and you get the recoil from the weapon hitting your shoulder or pushing back on you. The gun tries to push the bullet one way, the bullet tries to sit still and push the gun the other way. Equal and opposite forces. And I'll be using that reference later on. The other one I want to get across, and I'll save a few questions later, is give people a sense of scale about what turbulence is. Now, turbulence in airflow comes in all sorts of shapes and sizes. When we're flying in turbulent conditions, we're really talking about flying through eddies in the air that will range from this sort of size, meters, to tens of meters sort of scale. That's what it means when you're flying through turbulent air. You've got these big curls and movements of air in those sorts of scales. When we talk about turbulence coming from the back of the sailplane wing when you stall, we're now talking about eddies in the air with a range, size range of 1 to 2 centimetres up to around about 10 centimetres. Now, the size of your palm, eddies in the air about that kind of size, coming off the back of the wing, striking the fuselage, the tailplane, and so forth. And later on, when I start talking about turbulence in the sailplane boundary layer, I'm going to be talking about millimetre-sized eddies that are close to the surface of the aeroplane. So we're going from the very big down to, when we're talking about the drag on the aeroplane, to the very small. So what's a good definition of drag? It's really, in its basic form, how much we disturb the air as we fly through it. It depends on how much air we disturb and by how much we disturb it by. That's it in its purest form. So as we fly through the air, that's not the right slide. As we fly through the air, we're going to be pushing the air out of the way as we come towards it. As we move through it, we're going to be pulling the air back behind us again to close up the gap. We can't have a vacuum behind us. And as we move through it, we're going to get friction between the air and the surfaces of our sailplane. And I'm going to lump all that together as profile drag. So Newton's third law means that if we are pushing the air out of the way, then it is pushing backwards on us. If we need to pull the air in behind us as we fly, after we fly through it, then it is trying to pull us back as well. And if we have friction with the air, we're trying to pull the air along with us as we move through it. The air is trying to pull us back. Very simply, that's what profile drag is. So if we have smaller frontal areas, smaller, narrower fuselages and thinner wings, we need to push the air out of the way less than if we had a very thick wing or a very big frontal area on a fuselage. So the simple way of reducing drag from the profile drag is to push less air out of the way by having thinner structures, thinner, smaller frontal areas on our fuselages. So those kinds of things all have less drag. And you can see that with the modern sailplanes. We're getting thinner and thinner wing profiles. The fuselages are getting very, very cosy as they try and minimise the frontal area compared to some of the stuff that was found in the vintage gliders where you had quite roomy kinds of cockpits and very thick profiles on the wings. When we start talking about friction, we've got to start talking about boundary layers. And the boundary layer is that layer of air that's close to the surface of the aircraft that is affected by friction as we move through it. At the start of a smooth surface, as we fly through the air, we're going to have something that's called laminar flow. Laminar flow is interesting in that it has no mixing between the layers. If you have a streamline of air, it is going to be straight and follow the surface as one line. The really good thing about this is laminar flow, because it doesn't share the friction from the surface through that boundary layer very well, it's constrained to being very thin. We have very little air trapped in that laminar boundary layer. Less air being dragged along with us means less drag force applied to the aeroplane. After a while, that laminar layer will become unstable and it will become turbulent. So we'll get mixing of the airflow inside that little layer of air that's trapped against the surface of the sailplane. That then means more of the friction through the sailplane is spread throughout that layer of air, and you get more air being slowed down by that friction. The boundary layer gets thicker, more air being trapped in there, more drag force.
Boundary layer profile.
It is to a large degree. And the analogy I like to use is the Sydney Harbour Bridge analogy. You've got 6 lanes of traffic going across the Sydney Harbour Bridge. The outside guardrail is the surface of your aeroplane. For a laminar flow, you're going to get the far left-hand lane slowed down by friction. So it's going relatively slowly over the Sydney Harbour Bridge. The second lane is not slowed down as much. There's no exchange of friction between the first lane and the second lane. So it's slowed down a little bit, but not as much. And the last 4 lanes are not affected at all. Those 4 lanes are going quite smoothly at 60 kilometres an hour over the Sydney Harbour Bridge. But what happens to the traffic before it gets on the Sydney Harbour Bridge? Those 2 lanes are going slow. You're going to get some air, some of those vehicles changing lanes a little bit and moving around that blockage in the first 2 lanes. So that's what happens with the airflow as it goes over the airfoil for laminar flow. You get a little bit of that air that is being blocked by the boundary layer, shifting out a little bit, and it makes the airflow think that the airfoil is a little bit thicker than what it really is. But of course, when you get turbulent flow, you start getting the traffic that's slowed right down in that far left lane, changing lanes. It's mixing around with the other 6 lanes on the bridge. What happens to the amount of traffic flow over the Sydney Harbour Bridge when you get the slow guy changing lanes into lane 3 and then another slow guy moves into lane 2 and all that? What happens to the amount of airflow, the amount of traffic you get over Sydney Harbour Bridge? It slows right down, doesn't it? And it's a pain in the neck. And that's what happens when you get turbulent flow. You get some of that slow moving air changing lanes out into 2nd, 3rd, 4th lane, and some of that fast airflow starts to get into that boundary layer and share, and then it gets slowed down by the friction because that's the slow lane and so forth. You get much more of that traffic slowed down by that friction. And you've got more traffic, more air bogged down in that boundary layer. And it also then, of course, traffic further back before it hits the Sydney Harbour Bridge is going, hey, there's all this blockage. I can still get into lane 6 and go fast if I want. And you start getting the traffic trying to divert around the blockage, and it makes the airfoil look even thicker. But for drag purposes, you really got 5 lanes of traffic now bogged down instead of having 2 lanes of traffic. And that slows you back, that holds you back when you disturb the oar. If you're slowing the air down, it's trying to slow you. There's a hand up, was there? There's people. Aaron?
When you actually get blue,
Blue air. Why is it blue?
it's the language.
Yes, okay. So one of the problems with laminar flow in this laminar boundary layer is it's really sensitive. And it can turn turbulent from a variety of disturbances in the airflow. So gaps, bugs, dirt, rain, that kind of thing. So that's why with modern sailplane airfoils, we like to try and keep the front 2/3 of the wings as clean as possible. You're trying to remove all those disturbances to the airflow that are going to prematurely upset that laminar flow.
Is the laminar flow only over the surface?
No, the laminar
itself, the laminar, does it have laminar dimensions in its own?
Normally what we'll start talking about is the air in the outside world is relatively smooth, relatively being a measuring term, and most of the time when we start talking about drag, we start waving our hands around and talking about wind tunnels and models of wind tunnels and carrying on, where the air is absolutely made to be as smooth as possible. But for the general atmosphere, it's stationary, isn't it? And all of a sudden this moving object gets in the way and starts pushing it around. So the air, as it starts off, when it strikes the surface of our sailplane, whether it be the fuselage, tailplane, wing, it will have this property called laminar flow, where the flow is not exchanging friction between the layers. And after a while, for a variety of reasons, I'm keeping this as simple as possible, just accept that for a variety of reasons, it transitions, and that's the technical term, transitions into turbulent flow. Now, one of the properties of turbulent flow, in terms of sailplane-sized objects, is the turbulent boundary layer has about 3 times the drag of the laminar layer. And it's a simple reason, it's about 3 times thicker. Now, that's at sailplane scales. If you start talking about bigger objects, it's a slightly different number. But for tonight's purposes, talking about 18, 15 metre sailplane types of scales, we can simply say that turbulent flow, 3 times the drag of laminar flow. So with careful design of airfoils and fuselages, we can try and get as much laminar flow over the surface as possible. And that results in less drag. We've got less friction between the layers. We've got less air being trapped in that slow-moving lanes, less drag. One of the interesting things is laminar flow over the surface of the wing. That transition point, where it transitions to turbulent on the upper surface and the lower surface, moves around. It's dependent on the angle of attack. So as you increase the angle of attack, you're more likely to see that transition point on the lower surface move further aft to get more and more laminar flow on the underside of the wing. But the transition point will start to move forwards on the upper side. Because you've got the air flowing over the upper side of the wing faster, you've got more friction on the upper side of the wing. So it's not an even trade-off. And you'll often see, if you look in the technical manuals, that as you increase the angle of attack on a wing profile, the drag gets progressively worse. And that's simply because that transition point's moving forwards, you're getting more turbulent flow. It's on the upper side of the wing. It's got more speed and therefore more friction, more drag. And the range over these, the angle of attack range, where we get extensive laminar flow on both sides of the airfoil, so this low drag state the wing operates in, that's called the laminar drag bucket or the low drag bucket. That was accidentally found in the late 1930s by an organisation called NACA, which was the precursor to NASA, where they were doing wind tunnel tests on airfoils, and at that stage they didn't have any form of computing to derive the airfoil performance, and so they had rooms full of people doing the mathematical calculations trying to work things out. And as they were testing their designs in the wind tunnel, they came across a strange result. They found a region, normally around the zero angle of attack range, +1, -1 kind of angle of attack, where the drag suddenly reduced. And they called it the low drag bucket, and they had no idea what was going on. And it wasn't until the early 1940s that they really understood that there was this thing called laminar flow. One of the reasons why they didn't understand it is because up until the late 1930s, most of the aircraft had been fabric covered, and the fabric was rough enough to disturb the laminar flow having turbulent flow. It wasn't really a factor. By the time they started making metal aircraft, and the leading edge was one sheet of metal wrapped around, they started finding, hey, if we'll do this carefully, we can get this low drag state called laminar flow if we design everything really carefully. The other one was when they were doing these wind tunnel studies, they started trying to deliberately transition the flow from laminar to turbulent to see what happened. And they were using literally a piece of piano wire stretched across their wind tunnel against the surface of the airfoil to trip the flow. The reason why it got called a trip was because they were calling the wire the trip wire. So they were tripping the flow to turbulent because they had this trip wire mounted in the wind tunnel. That's where that got its name from. So back on topic. Older sailplane airfoils like the Wortmann FX series, which were the early generation of laminar drag airfoils for sailplanes, had very wide low drag buckets. They covered a very large angle of attack range, pretty much from very close to a lift coefficient of 0 all the way up through to very close to stall. Then Champerth brought out the discus, and this was a bit of a revolution because what they did was they limited that low drag range to a very discrete set of angles of attack. One was your climb speed, the other was your cruise speed, and beyond that, they didn't really care. The advantage they got out of that by limiting that angle of attack range was they made the laminar flow very extensive over the wing and got a very low drag airfoil out of the as a result of that. What it does produce though is, and I'll show a couple of curves at the end, you'll get a distinct kink in the L&D curve, the performance curve, where you'll see the curve follows a shape and then it'll just drop off in terms of its performance. And that's because you're dropping out of that low drag bucket, that laminar drag bucket, and you've got quite a bit of turbulent flow on the underside of the surface. The angle of attack's too low and the transition point's scooted a long way forwards. Excuse me, I'm not used to using the touch screen here. So boundary layer separation. One of the problems with laminar flow is it's very sensitive to disturbances, and it's also very sensitive to slowing down. One of the analogies I also like to make is the airflow is a bit like a garden hose, particularly laminar flow is like a bit like having a garden hose. It's a bit kinky, a bit wobbly. If you continually try to accelerate that flow and keep it going faster and faster and faster, it's a bit like pulling on that garden hose, and it stretches all the kinks out and it keeps the flow laminar for longer. But what happens when you try and slow down that garden hose once you've got it fast and you start trying to push on the garden hose? It kinks up, it goes turbulent. And one of the problems here is if you have the laminar flow stretched out too much, when you try and slow it down, it won't follow the surface of the wing anymore. It separates. And that's called a laminar separation bubble. It will form a bubble against the surface of the wing. When it does form that bubble, the laminar flow that's going over the top of the bubble will transition to turbulent flow. The turbulent flow, because it's exchanging low-speed air for high-speed air throughout its depth, is able to handle that slowing down process a whole lot better and reattach and follow the surface again. But in that little area where the laminar flow has detached and then reattached, you've got this little trapped pocket of air, a laminar separation bubble that's trapped against the wing. Those things are very draggy. It's a little bit like having your air brakes partly out. And it's around about 9 times the drag of laminar flow. Again, this is sailplane kind of dimensions. So it's 3 times that of the turbulent flow. So that's 9 times that of the laminar flow. And that does very much depend on the size of the bubble. So this is a wind tunnel picture. It's not a glider airfoil, it's just a stock standard airfoil. Airflow is going from right to left, and you've got the smoke lines in the air to show the streamlines. Now, is my mouse going to show up on the screen? No, it's not. Right. You can see a point marked there called separation point, where the air is no longer actually going to follow the surface of the airfoil. And you've got that dark area trapped underneath, which is what's called the separation bubble. That is a pocket of air that's circulating around underneath the airflow, trapped up against the surface of the wing. It's not a vacuum, but it's still quite low pressure. And because it's now on the back half of the wing, it's trying to suck you backwards, effectively. And it's also making that airfoil look to be a whole lot thicker than what it really is as well. Somewhere about where the bottom of the arrow for separation bubble is, it will start to go turbulent. And one of the things you can see is the smoke lines become very indistinct. They're no longer clean lines. It's all being smeared out because that air is now being shared around throughout that boundary layer. In the front half of the wing, you can see the streamlines are all quite close together. The boundary layer is just below the point of the end of the arrow called separation point there. But you can see that the turbulent region is about that deep. And you can see that the smoke's being shared and smeared out throughout that layer, showing turbulent flow. But it's that bubble of air that we're pulling along behind us that's really causing all the drag. Yes, Eric?
Do you have any equivalent pictures of any of the airplane sections?
No, unfortunately, look, this is what I can grab here and now at the time. And this is an old NACA airfoil. It's probably a 4 series airfoil that was just pulled out of an archive from a university study. Finding really good photos like this for sailplane airfoils is incredibly hard to find, unfortunately. And I don't have a wind tunnel to do it all myself. If you want to donate the funds for me to have a wind tunnel, I'd be more than happy to receive the funds.
Especially the 103, it's likely with that. So the whole dust build up in front of it, and then just behind the spars area there, you can see a patch of it, and I do it for the separate, done the separation bubble area. But there's no doing it, it's just sort of
quite likely, yes. And most airfoils will have some form of separation bubble depending on what size and speed they're operating at. It is a bit of a feature of that transition from laminar to turbulent flow. It's just a matter of how big and bad it is. So most of the sailplane airfoils around the place will have a small one, whether you like it or not. And because the transition point will move forwards and backwards depending on the angle of attack, you might find that there's an angle of attack that will appear, the transition point will move forwards, it'll be turbulent flow, and therefore that bubble will disappear. It just depends on the angle of attack they're operating at. But it is a case of just how severe, how bad is it? So the way that we can avoid separation bubbles is by deliberately tripping the laminar boundary layer to turbulent ahead of where the separation bubble forms. And we use that by using turbulator tape. The whole idea is that having the turbulent flow at only 3 times the drag of laminar flow is a whole lot better than having the separation bubble at 9 times the drag of laminar flow. So you're trading off a little bit of laminar flow, but you're avoiding separation bubble. So the turbulator tape either has dimples or zigzags, and that's to induce little vortices in the boundary layer and encourage that mixing between the slower layers and the faster layers to have that speed sharing. Some manufacturers have little blowholes. The purpose is exactly the same. They're trying to get the air that's in that laminar boundary layer, it's a few millimetres thick, start to mix around a bit and share the higher speed air with the lower speed air down the bottom and vice versa. It's far better at slowing down more equitably. As I said before, the turbulent boundary layer is far better at avoiding separation. Now, turbulent boundary layers can separate, and once they separate, they will not reattach to the surface. And everyone here in this room has experienced them. That's what happens at stall. Right? So all that buffeting and high drag state you get at stall is the turbulent boundary layer separating from the trailing edge of the wing. However, with turbulator tape, the positioning is absolutely critical. If you have it too far aft, the tape won't have trip the flow soon enough, and you still get the separation bubble forming. If you have it too far forward, you will have avoided the separation bubble, but you'll have, again, a lot more turbulent flow where you could have had laminar flow, have more drag that way. So if you are going to change out your turbulator tape, make sure you know where it's supposed to be from the manufacturer. I've known a few people who have ripped off the old turbulator tape, cleaned up the wing. Now, where did it go again? Particularly if you're going to go and do a refinish on an older sailplane, take the gel coat off. So there's absolutely no hint of where the gel, of where that zigzag tape used to be. And it's far better off getting the correct location from the manufacturer, because you're not quite sure if a previous owner or a second-hand sailplane's got it right in the first place either. You'll be surprised at some people going, that's about right. It was about there somewhere.
What is the best way of determining where to put the turbulate?
One, ask the manufacturer. Two, if you suspect you have a separation bubble problem, you can do your own little bit of flight testing, but it involves getting some grotty old sump oil or something like that, something black and viscous, and smearing it on your wing, and then going for a fly at the speed at which, or the angle of attack at which you think you're getting it. And then you can look at the pattern on that oil, a bit like Frank's dust, to see where it's been smeared out, where it's been trapped, and where it's sort of beaded, which will show you laminar separation bubble turbulent flow. It's a bit of a pain in the neck, and it makes a mess on the glider, because to optically see it and have something left when you, by the time you arrive on the ground, you need some really awful old sump oil to do it. Can be done. So out of profile drag, the wing is the largest surface area on the sailplane. It will produce the most profile drag. This is why when we do use the drag equation, there's that S in there. It's the wing surface area. It's our reference area for that. I mentioned before that the air is moving faster over the upper surface and therefore has proportionally a bit more drag than the lower surface. Tadpole fuselages have less surface area. Now, there's a lot of fuss that happened when people started using tadpole fuselages, this hot and boom design that first started coming out with the first generation fiberglass aircraft. The vintage aircraft all tended to come up to a maximum thickness and then be linear back towards the fin. And in the 70s and 80s, there are a number of studies done, and instead of using frontal area to calculate the drag coefficient of the fuselage shape, they use the wetted surface area. And they show that the majority of the drag reduction of these tadpole fuselages was quite simply a smaller surface area. You have less surface area, less air trapped in the boundary layer, less drag. There was a little bit about laminar flow there, but not very much. And this sort of knowledge was actually known about by the end of World War II. You see all these late World War II piston engine fighters were coming out with bubble canopies. Early World War II aircraft all had a big fairing behind the canopy back to the tail. They all went to the bubble canopies because that reduction in the wetted surface area on the aft fuselage was causing the less drag, they could go slightly faster. That was the answer. There was also visibility issues, but then by the time you have a big bit of armour plate back there and a few other bits and pieces, looking around behind you was pretty hard. But it was a twofold increase. You got improved visibility, but you also got less drag out of it as well. And it's just the reduction in the wetted surface area. And the take-home message here is profile drag is proportional to the square of your airspeed. If you fly twice as fast, you'll have 4 times the amount of the profile drag. So we'll move on to induced drag. Unfortunately, this is a side effect from producing lift. And this is where, again, I mentioned Newton's third law. If we take air and it is pushing up on the surface of the wing to hold us up against our weight, we must be doing something equal and opposite to the air as well. So we must be pushing the air down in some way, shape or form. So this is how we produce lift. We take an amount of air and we push it down behind the wing. So we end up having that conservation of momentum, we produce lift. The way that force is distributed onto the airfoil is by a lower pressure on the upper side and a comparably higher pressure on the lower side. That's how that force gets distributed onto the actual surface of the wing and transmitted to the aeroplane. But we've got a choice. We can take a lot of air per second and push it down a little bit to produce lift, or we can take a little amount of air per second and have to push it down a lot to produce the same amount of lift. That's what we're going to be talking about next. So Newton's third law again, a representation of an airfoil. We have the air coming at zero angle attack in that particular picture, and we've got the air moving down behind the wing at a slight angle. The downwards component of that is called the downwash, and the angle that it forms with the horizontal there is the downwash angle. The reaction force we get on the airfoil is that thick arrow. We have the lift component, which is the component which is perpendicular to the original airflow. That's the component straight up. That's what we call lift. And then we have a small amount of that lift reaction going back horizontally. That is our induced drag. Doesn't take too much to work out that if we then have to slow down and increase the angle of attack as a result, we are going to have an increased amount of downwash behind the wing. We're going to rotate that reaction force further backwards. We're still going to be measuring lift as in perpendicular to the original airflow, so perpendicular to horizontal. And the induced drag component is a whole lot more. The lift force here is measured in terms of our lift coefficient. The lift coefficient we get is actually related to the amount of downwash, or that angle we deflect the airflow through. The induced drag is therefore a factor of the amount of lift we're producing multiplied by the angle that we deflect it by. And the angle between the lift and that reaction force is actually half of the downwash angle behind the wing, by definition. So the induced drag ends up being the lift multiplied by the lift. So it's lift squared, CL squared. And for those familiar with the induced drag equation, that's where it comes from. That's how we work out that component. At the wingtip, we have something funny going on. We have the air that is behind, that gone over the wing being pushed down. The air that's outside the wing is effectively undisturbed, and it tries to move up and spill over the top of the wing. The air that's under the wing tries to move out, and you end up getting a spiral pattern behind the wingtip. This is what we call a wingtip vortex. The energy contained in that wingtip vortex as that air is swirling around behind the wingtip comes from the sailplane. It is proportional to the downwash, and it comes from our energy moving through the air. So it's robbing energy from us. The stronger that vortex is, the more energy it's stealing. This vortex is a significant component of induced drag. So if we can reduce the strength of this vortex, we're going to reduce our induced drag by a reasonable amount. So we've got a couple of happy snaps. These are not my photos. This one here, the airliner has just skimmed the top of that cloud. The cloud was an elliptical shape, and the two sides of that cloud would have been joined over. We can see that the centre of that cloud has been pushed down by the downwash behind the wing. And we can see there's some very strong vortices coming off the wingtips and the end of the flaps, twirling the ends of the cloud around. A similar photo, you've got some very strong vortices coming off the flaps of the A330. What's interesting though is you can see the traces of fog being drawn in from a fair way outside the aeroplane and pushed down between the two vortices. So you can see the air coming from right to left and from left to right, and then being drawn down into that vortex. You'll see that the vortexes do become unstable some distance behind the aeroplane and start to break up and dissipate. So mathematically, you can say they go on forever, but in reality, the airflow breaks down and breaks up. Sorry, I've double clicked again.
So the butterfly effect is about the butterfly effect.
Yeah, the butterfly effect can be real, except you've got to be a close distance to the butterfly. The butterfly flapping its wings in Amazon is not going to cause thunderstorms in Africa. Viscosity gets in the way. Unless you have a really, really big butterfly. For those interested, the amount of air we're moving around the place is proportional to the chord of your wing. We're normally talking about the air 4 or so chords above the wing, 4 or so chords below the wing is being affected by the wing, and about 4 or so chords ahead and a bit further behind. But it's proportional to the chord, which makes a bit of sense then. If we're pushing the air down, it gets pushed down by about 3 or 4 chords. So if you get to within 3 or 4 chord distances with the ground, something funny happens. That downwash starts to hit the ground and the wingtip vortices break up prematurely. And that's what's called ground effect. And all of a sudden, your L on D improves remarkably and you can float along the ground at remarkably low speeds for a remarkably long way because your induced drag, your low speed drag, is drastically reduced by having the ground so close to your wing. And the bigger the chord of the wing, the more of an effect you get. So some of the old vintage gliders, particularly the old 2-seat gliders with these very big root chords with a mid-wing design, you can get down to within 1 chord of the ground with that wing. It will ground effect a very, very long way. So induced drag. A high aspect ratio wing simply takes a greater span of air and needs to push it down less to make the same amount of lift as a low aspect ratio wing of a similar area. Okay. The induced drag is proportional to the square of that downwash velocity. So if you have a high aspect ratio wing, which is taking a greater sample of air and pushing it down less, you're going to end up with less induced drag. You can take twice as much air, push it down as half, you end up with a half squared, which is a quarter, times twice the air, still 1/2 the drag. So by doubling your aspect ratio, you're going to half your induced drag, which is why sailplanes have these phenomenally high aspect ratio wings and keep on trying to push that aspect ratio higher and higher. It reduces your induced drag. If you fly twice as fast, you're going to have twice as much air over the wing. You have half the downwash. Induced drag is square that half, so it's a quarter. Even though you've got that, you've got 1/2 the induced drag. So force that, I'll go back again. You've got half the downwash, you've got 1/4 the induced drag. So you've got this inverse relationship with your speed. If you slow down, if you go half as fast, you've got 4 times the induced drag. So the induced drag is your low speed drag problem. Back into the 1920s and 1930s, there are a lot of mathematical studies going on about how wings produce lift and producing a mathematical theory of how wings work. And they didn't have computers back in those days. They had rooms full of people doing hand calculations, very mandroid process. And they worked out through a number of approximations and a number of simplifications that the wing plan form has quite an impact on your induced drag. And you often see it in the textbooks that the induced drag equation has an efficiency factor, an E factor, sometimes K. The mathematical solutions they came up with in the early 30s said that with these simplifications and approximations that they used, that the ideal wing plan to minimise induced drag was elliptical. Hence, you got the design of a number of classic aircraft from that era, like the Supermarine Spitfire there, with an elliptical wing. They are going all out to try and minimise the induced drag, particularly for a dogfighting aircraft when you're turning and burning or producing a lot of induced drag when you're loading up the airframe. There's a number of features of this wing plan form. One, the wing has a constant lift coefficient across the span. It can produce a sudden stall if you have a constant airfoil with a constant maximum lift that it can produce. If you've got a constant lift coefficient across that span of wing, it's going to hit the stall point all at once. And that can produce some rather unfortunate handling characteristics. And you can see it in the Spitfire. It's only got 1 degree of washout. And when you see the Spitfire landing, it will flare in the 3-point attitude, hold off, and then it will just drop on the ground and bounce. That's because the aircraft is stalling pretty much all at once. This doesn't mush on like a lot of the straight wing airplanes. The main disadvantage of an elliptical plan form in terms of manufacture, it's just damn difficult to make. But when we start talking about plan form efficiency, this extra factor that they put into the induced drag equation, it depends on the wing shape. So rectangular wings, and again, this is a simplification and approximation, have an induced drag efficiency of around 86%. Rectangular wings are very easy to make. It's the same rib all the way out. You just mass produce the ribs. They have a very benign stall characteristic on the plan form. The stall starts at the root, works its way outboard. You retain aileron control all the way through the stall. Very mushy, great for a training aeroplane. And very cheap to make. Single tapered wings with a little bit of wing twist, you get up to 92%. The double tapered wings, K21's the classic there, Birdcraft 4, Boomerangs, just about a lot of those, that era of aircraft have 2 tapers to the wing, 97%. The wing twist can mess it around a little bit. At low angles of attack where you've got a low lift coefficient, that wing twist starts to work against you and that efficiency drops right off. But at high speeds, low angles of attack, you don't care about induced drag. It's not really a factor. You're more worried about the profile drag. Multi-tapered wings, so this is tapered wings with 3 or 4 or 5 panels on them. You're getting pretty close to that ideal elliptical shape and you're getting 100% efficiency. One of the things to remember is that induced drag equation that you see in the textbooks all the time. That is a simplification. There's a lot of things done in the making of that equation to make it neat and easy to fit in the textbook. And one of the things that they did was to assume what's called a planar wing. It only exists in 2 dimensions. It's got span and it's got chord. It doesn't have any dihedral. And winglets can be assumed to be the end of the wing with 90 degrees of dihedral. And that equation does not account for those things very well at all. So where you get these modern sailplanes with these multi-tapered wings and you see the dihedral being fed in elliptically, so increasing it with span, so you get a bit of a curve on it, you can actually get better than 100% efficiency in that drag equation. It's because the drag equation has been simplified. It's not that you're getting perpetual motion out of your wing. People get a bit hung up on that. And the same thing can happen when you start putting winglets on sailplanes. If you had a double tapered wing with the wing twist, you've got 97% efficiency. If you get an extra 7 or 8% efficiency out of having a winglet on your end of the sailplane, you're up to 104, 105% efficiency. Hooray, perpetual motion. Doesn't quite work like that. So how do winglets work? All the winglets you'll see on sailplanes are on the upper surface. They have downwash behind them, just like the regular part of your wing. It's trying to push the air outboard from above the wing. Now, if the air is trying to form a vortex, it's trying to spiral over the wing and move inboard on the upper surface, and you've got the winglet trying to push that air back outboard again, it's going to weaken the effect of that vortex. The net effect is that vortex gets smeared out over the height of the winglet. So taller winglets are actually more effective, more efficient. You're smearing the vortex over the height of that winglet. The downside is you're adding more profile drag to the aeroplane. This is where the trade-off happens. You need to try and balance your reduction of the induced drag with the increase in your profile drag. With the modern sailplanes, with that kink in the polar curve at about around where the cruising speed is, you end up having that trade-off point being net zero at about that kind of speed, because you're not worried about what's happening on that kind of speed. You're not going to be operating cross-country at that kind of speed at all, and you get the maximum benefit out of your low-speed end that way. But it does make me think a little bit. With all the modern sailplanes, they're being designed for competition use. Wouldn't mind betting as we get into the future, we might see sailplanes coming out with 2 or maybe 3 sizes of winglet. And that if you see a day for a week forecast, you'll see people fitting the big winglets on, because that's giving you the best low speed advantage. You're spending more time thermally, you're going to get more advantage out of having taller winglets. And if you're having a very strong day, you might find people putting small winglets on, because you're going to be spending more time cruising, less time climbing, and you'll get more benefit that way, less profile drag. Just a thought. The effect of doing that won't be much, but it's only going to be 1 or 2%, but competitions are won and lost on 1 or 2%. So there's a trade-off with winglets. The other factor is, because you've got less cross-flow out of the wingtip, what I mean there is, as the air is spilling over the top, it's starting to push the air inboard on the top surface. It's trying to suck the air outboard on the undersurface. The air is no longer going chordwise over the wing. It's not following the airflow as it was designed. And so the airflow doesn't work as well as it should be, because you've got the airflow going in different directions. By putting a winglet there, you're reducing the strength of that vortex. You're not getting so much of that airflow going across the span. It's going along the chord. And so you're going to get more lift out of the wing, and you're going to get better controllability out of your ailerons being out there at the end of the wing as well. The downside is, if you're getting more lift out there at the end of the wing, you're going to get more bending on the wing as well. And that's one of the reasons why retrofitting winglets onto the older designs can be problematic, is they're not designed to handle the extra bending of all the extra lift out on the outboard section of the wing. The other one's flutter, but that's a different story for a different day. So we get some other types of drag we can encounter. One's interference drag. That's normally where you get surfaces coming together, so the wing joining onto the fuselage, the tailplane joining onto the fin. And that's where you get the boundary layers overlapping, so you get the air being slowed down by more than one surface. Mathematically, if you were to take the wing separately and work out the drag for the wing, and the fuselage separately and work out the drag for the fuselage, and add those two together, the drag of the whole sailplane would be more, because you've got those corners on the airframe where you get the air affected by both surfaces. That's that extra little bit of drag you get there. The classic one being the standard label on the underside, where you've got the fuselage coming at quite an acute angle to the wing. You get quite a pocket of air that's affected by the fuselage and by the wing surface trapped in that acute angle. All the modern sailplanes have a very generous a radius in there to try and smooth that area out. They're also using a unique airfoil in that region, so that the airfoil performs better in that region that's been affected by the fuselage, and you'll see that on your aircraft quite pronounced. It's going to be quite a different airfoil shape close into the fuselage, than maybe half a metre out from the fuselage. Yeah. So gone are the days where you have one root profile and one tip profile, sort of morph it by some arcane method out. You've got multiple airfoils being used depending on where it is on the wing to suit the conditions that that part of the wing experiences. The other one there is the horizontal tail where it joins onto the vertical tail. You often see a radius there of some kind to try and minimise the interference drag. The late model PIC 20s, I think they tried to mount the tailplane further forward on the fin to try and reduce the amount of air that was being trapped in those corners, those kinds of things. Extra drag, you can get drag from antennas, air probes, windows being open, air leaks, undercarriage door gaps, that kind of thing. Most of these are simply disturbing the boundary layer, making it thicker, trapping more air up against the fuselage or the surface, and therefore you're getting more drag. Air leaks into laminar flow will cause it to become turbulent. Remember I said about the little jets doing the same thing as that. So for fuselages, the first half to 2/3 of your fuselage up past the cockpit is probably going to be laminar flow. By the time it gets to about 2/3 of the way down towards the wing, it's starting to transition there somewhere. Things like the yaw string will cause turbulation. You see a lot of people either trying to move the yaw string further back on the canopy to try and delay the point at which it trips the airflow. Air leaks around the front edge of the canopy does the same thing. So sealing the front half of the canopy really well helps a lot in maintaining laminar flow over that first half of the fuselage. People have gone to some great effort to try and seal up air brake boxes so you're not getting air leaking out through the wing root, down the wing and out through the air brake box, causing transition of the laminar flow over the wing there. A lot of people now have cabin air exhausts trying to suck air out of the cabin, making the air vents work a little bit more efficiently, but what they're trying to do is really controlling where that air is leaking out of the airplane in a controlled manner, so it's not leaking out where it shouldn't and causing more drag that way. So when we add the two together, we end up with what's called a polar curve. The green line is the induced drag, the dashed blue line is your profile drag, the red line is the sum total. The minimum sink speed is where your minimum drag occurs, and that's where you've got 50% induced drag, 50% profile drag by definition. From that, we can work out what our sink speeds are. And there's a number of different profiles. I recycled an older presentation. So these are old two-seat gliders. So Janus K21, Twin Aster Bergfalk for some relative performances there. These are old school polars where you've got a pretty constant curve. Some of the more modern ships you'll see that up around 85 knots or so, there's a distinct drop off, a very sudden drop in the performance of the aircraft where the airfoil transitions to turbulent flow on the underside. And the good side is they've got really low sink up to that point and that goes terrible. So any questions? And this is a photo that I took somewhere in the middle of the Southern Ocean. If you look carefully at the photo, the front half of the Albatross there has very smooth feathers on its forward fuselage, and that's to try and maintain laminar flow in a low drag state. There around the centre of its belly, there's a whole range of rough feathers, and that's turbulator tape bird style. So they're tripping the flow to turbulent flow. So as it comes around the back of the bird, you've got that higher pressure air on the surface that's facing forwards and pushing against the bird to reduce the drag that way. So they do have turbulators on wildlife. We're just copying them. And you can see that the wing tends towards that elliptical kind of wing plan form as well. High aspect ratio wing. It's a soaring bird, so it's trying to reduce the induced drag and control its profile drag.
So
you explain why they use this to market?
I don't honestly know is the real answer. When they first started doing this, they were plotting these drag curves out on a graph, and they had lift coefficient going up the vertical axis and drag coefficient going across the horizontal axis. And they were getting a C shape, some sort of curve for the drag. And then they would suddenly get to a point where it would form like a rounded rectangle with low drag off to the left around these low angles of attack. And that's called it the low drag bucket.
That is the region where you have the idle.
That was the region where they were getting reasonable amounts of laminar flow over the upper and lower surface of the wing. And they just fell over it one day. The first laminar flow production aeroplane was actually the B-24 Liberator bomber. The guy who designed the wing of that was, I think his name was Peter Davis. He was a self-taught aerodynamicist. He was very much a truth is beauty and beauty is truth kind of person who believed in ideal mathematics. And the way that they were designing airfoils back in those days was what was called mathematical transformations. They had a mathematical equation that described the flow around a cylinder. And you could describe that flow for if you had like an angle of attack on it, things like that. So they could do that mathematically. And so what they were then is they are stretching that cylinder out into an airfoil shape mathematically, and then plotting the airflow using that same stretching out mathematics. And he ended up coming up with an airfoil that he happened to like. And he ended up designing for its day, quite a high aspect ratio wing around it. And he went trying to sell his design to the aircraft manufacturers in the US. Consolidated was competing with Boeing at the time. Boeing had already flown their B-17 heavy bomber in 1935, 36. So this was the American equivalent of the Lancaster, which first flew in 1942, but they were flying the B-17 in 1935. So the Americans, in terms of bomber technology, are pretty advanced. And Consolidated were looking for an edge. They were trying to look for a gimmick, a sales factor that they could try and one up over Boeing. So they bought Mr. Davis's design and put it on the B-24. Unbeknownst to anybody at the time, it had one of the reasons why it had this low drag wing was it had laminar flow over quite a section of the wing. The first 25% of the chord or something was laminar flow. Produced a bomber that could cruise a long way in this laminar flow region if they managed to establish it. It had a few downsides. It didn't take damage tolerance very well. That laminar flow, when it hit a bullet hole or something, that formed separation bubbles and all sorts of horrible things. And then the aircraft became very draggy and hard to control. But that was the accidental first aircraft with a laminar flow wing. The first aircraft designed with a laminar flow wing was the P-51 Mustang. And that's where the engineers at NACA, which was a government organisation, was publicly sharing its information. North American Aviation were trying to sell an aeroplane to the British. The British were looking for fighters at the time. And they said, hey, here's a fighter for you. And, oh, by the way, it's got exceptionally long range if you cruise at this particular speed. And that was the first deliberately designed aircraft where they knew they had a laminar flow wing over a certain cruise range.
The glossier the surface, the better.
So what was that?
The shiny and glossier surface.
Yes. Disturbances to the airflow will create more friction. You will get transition to turbulent flow earlier. So keeping bugs and things off, rain, water droplets are classic ones for that. But keeping it polished is far better, and more on the front half than the rear half. So keep the front half of your wing polished more than your rear half.
it's a double shine, it ain't mine.
Something like that. Anything else? So, Craig, did I achieve the goal?
Well, I've got to say that it's a fantastic presentation because not only was there one improvement moment for quite a few, particularly the separation of it, we got a very clear understanding of it. So it's been excellent presentation. Thank you very much indeed. So please thank you. And